So we'll pick up the lecture where we were last time, and we're talking in general about boundary conditions for mass transfer. So I'm going to try and wrap this up very quickly. We didn't have very much to go to finish up this section. Remind you that the general problem we're considering is one where we have an impervious phase of material that is contacting another phase, so a gas or liquid phase that has components in it that can diffuse to this interface between phase 1 and phase 2, can undergo chemical reaction, can adsorb on the surface, and can be transported through potentially boundary layers that are near the surface. So this has all of the near surface effects turned on for mass transfer, and can be a model system for catalytic surfaces. We were considering the last case of the in the notes, and that's a case where we have flow in phase 1, that is in the fluid phase, dominated by convection. And in this case, it's very typical to define the mass flux in terms of a mass transfer coefficient Km, and to write that mass flux in terms of a driving force, which is the difference between the concentration of A far from the surface, that is in the bulk, minus that at the surface. We'll learn later on in boundary layer theory how to actually calculate these mass transfer coefficients. As you might anticipate, they'll depend on things like the Reynolds number and so forth. This is in direct analogy with the way one might define a heat transfer coefficient for how the heat flux depends on temperature difference in a system where convection is important. And so we want to think about, as the last example, a case where we have first order chemical reaction and adsorption and desorption going on at the same time, with potential limitations due to boundary layer transport. And at steady state, the flux across the interface, then flux of material to the interface, has to be exactly balanced between these three, if you will, resistances to mass transfer. One being the transport through the boundary layer to the surface, the other being the uptake of A by chemical reaction, and the third being the adsorption-desorption equilibrium, which we've written in this way. And so where we were last time when we stopped was at this point where we can rearrange the expression on the previous page to finally isolate the concentration of A at the surface in terms of the concentration of A far away from the surface. These various rate constants give us the rate of mass transfer through the boundary layer, rate of chemical reaction at the surface, and so forth. And so this is a useful result in the sense that it allows us to relate the concentration of A at the in phase 1 at the surface to its concentration in the bulk phase. Very typically, what we can measure in these experiments is the concentration in the bulk. The concentration right at the surface is often important for the molecular transport processes and for reaction, and so to be able to relate those two to each other is important, to be able to connect what we can measure practically with what we're modeling at a molecular scale. We can in this sense, if we can connect the surface concentration with the bulk concentration, we can write the mass flux as shown here in terms of an overall mass transfer coefficient K times that bulk concentration. You can use this result together with the ones that are shown above, and after a bit of algebra you come to the equation at the bottom of the page, and this should be vaguely at least familiar to you. It is essentially saying 1 over the overall mass transfer coefficient given here depends upon contributions from the adsorption-desorption equilibrium, chemical reaction, and also mass transfer through the boundary layer. This, you may recognize, is an example of a resistance in series model. In other words, you have a resistance to mass transfer in the boundary layer, a resistance to mass transfer associated with the adsorption-desorption equilibrium, and then a resistance to mass transfer associated with the actual kinetics of reaction of A on the surface. And this model captures all of those resistances in series. The last page just talks about what happens when one or the other of these resistances are dominant. And in typical problems we'll be working with, we will be in situations where you don't need to include all of these effects together. Often one phenomena or the other will be dominant. This is an example where if the chemical reaction rate constant K hat is small, then the resistance due to chemical reaction, resistance to mass transfer, will be dominant, and the mass flux will be equal to the rate of chemical reaction of A on the surface. The other two resistances, the adsorption, desorption, and the transport through the boundary layer, are unimportant. If the resistance to mass transport is dominated by boundary layer transport, then the mass flux turns out to depend only on that mass transport coefficient and the concentration of A in the bulk. And you can work your way through the last version of this as well. So this gives us an idea of the various boundary conditions that we'll use in solving mass transport problems. We'll apply this probably starting, I would say, next week when we get back to looking at detailed solutions to specific problems. The next section in the notes is one related to essentially multi-component transport, and it is extending the results that we've been talking about to situations involving more than two components, so three or more components, and situations where the driving force is other than simply a concentration gradient driving force. The basic notion behind this is that mass transport, although we very typically use Fick's law as a starting point where the flux is proportional to a gradient in concentration, we can think more broadly that the mass transport is driven by gradients in chemical potential. And the chemical potential of a component in a mixture can depend on its concentration. This gives rise to just the common form of Fick's law diffusion. But the chemical potential of a component in a mixture can also depend upon pressure and can be influenced by external forces like gravity, what are referred to in the literature as species-specific body forces. So if you have an ion like a sodium ion in an aqueous salt solution, you apply an electric field to that solution, and the sodium ions will migrate in one direction, and if you have and the anions, chloride for example, will migrate in the other direction. And that's an example of a species-specific body force. Another example would be if you have magnetic particles in a mixture and you apply a magnetic field across that mixture. This can cause diffusion or migration or mass transfer. And so the results that we'll present today in this section provide a more general form of the constitutive equation that relates mass flux to the driving force for mass transport. And the interesting thing about this is that we really don't have a fundamental all-encompassing theory for this. So the results that I'll present to you, which follow closely what's in your textbook on this, come to us from kinetic theory of gases, and it's derived based on the notion that the mass flux is driven by gradients in chemical potential, and then how does the chemical potential depend on concentration, pressure, temperature, and so forth. By far, the most important form of mass transfer in chemical engineering type problems is that driven by concentration gradients. And so we'll wade through some of this at least a high level, but never forget that ultimately what we come back to using the vast majority of the time is that mass transfer is driven by concentration gradients. And so what this framework provides us is a thermodynamically consistent framework for describing how the driving force for mass transport affects the flux. And so the basic result from kinetic theory, which we're not going to derive here, is shown at the top of the page. And it has the mass flux written in terms of gradients in temperature. The d sub at is a so-called thermal diffusion coefficient, so gradients in temperature in a system can drive mass transport. And unlike the diffusion coefficients that we normally see in Fickian diffusion, these thermal diffusion coefficients can be either positive or negative. There are situations where if you heat a mixture up, it will cause one component to migrate in the direction of increasing temperature. The other components will migrate in the direction of decreasing temperature. And so these thermal diffusion coefficients as a result can be positive or negative. Diffusion coefficients associated with other types of gradients like concentration, pressure, and so forth can never be negative. It turns out that at a fundamental level it violates the second law of thermodynamics, which is not a good thing to do on a regular basis. And so this writes the mass flux in terms of gradients in temperature and in gradients in the so-called generalized driving force, d sub a. This generalized driving force is basically gives the effect of chemical potential on the effect of concentration, pressure, and these species-specific body forces on chemical potential. Again, by far the most important one will be the one involving the effect of concentration on chemical potential. And what you see from the initial picture here is the terms in the summation or the gradient and the chemical potential of component A with respect to the composition of each component in the mixture. And so this allows for the possibility that a gradient in concentration of one component can actually influence the chemical potential of another component and cause that component to migrate as a result of that coupling. It also gives us a systematic way to introduce the effect of pressure on diffusion driving forces. Of VA bar here is the so-called partial specific volume of component A. It is the mass analog of the partial molar volume, so how much volume component A occupies in the mixture, and rho is the mixture density. We'll come back later as we need to talk about the detailed form of these species-specific body forces, F. In the case of gravity, it's just the mass of the component times g. In the case of electric field-driven transport, these species-specific body forces will have the valence of the component in question and the electric field potential and so forth. For magnetically driven transport, there'll be yet another form for these terms. It's possible to show, and in fact you get an opportunity to do that in the homework, that the sum of these generalized driving forces is equal to 0. I'm not going to belabor that here since you have a chance to work your way through that. The book that has really the most comprehensive explanation of this phenomenon is one by Hirschfelder, Curtis, and Bird, and that's the same Bird that is the co-author of your textbook. It's about this Hirschfelder, Curtis, and Bird is a stat mech book on transport phenomena. It's about 3 inches thick and is a great reference source for the fundamental theory in this area. We don't use it in this course really because we're more interested in practical problem solving, but this is how you get back to the fundamentals of the theory in this area. And in there you'll find a derivation that shows that these multi-component diffusion coefficients that appear in the generalized driving force expression for flux are equal to 0 when the coefficient on them is equal to, are the same. The issue that we face as we move from a binary system, so just 2 components, to one that includes 3, 4, 5, or hundreds of components, is that the number of effective diffusion coefficients that you need to describe that system literally explodes, and I'll show you that in just a moment. And so it becomes incumbent on us to look for ways to find relationships among those diffusion coefficients to to the greatest extent possible in order to simplify the experimental effort that you would need to fully populate a model such as this. We can also show that since the sum of the diffusive fluxes in any system has to be zero, that the thermal diffusion coefficients have to add up to be zero in a case where you have thermally driven diffusion. And this means, for example, in a binary system, that if you have only two of these thermal diffusion coefficients, one of them is always positive and one of them is always negative, reflecting components that migrate towards high temperature regions and away from high temperature regions in a mixture. We'll do some thermal diffusion calculations a bit later on so you see better about how this operates. It turns out that the second term, in order to satisfy this constraint, it has to be satisfied rigorously when the only gradient is temperature, and also satisfied rigorously when there's no gradient in temperature, and so that leads to these two conditions that have to hold under all circumstances. We can write or pick out one of the generalized driving forces, that is d sub A for component A, and we can write it in terms of all of the others. If we put that back into the relationship at the bottom of the page, you get a relationship shown here in equation 7. Since these driving forces can be varied independently of one another, you can set concentration gradients for specific components. You can set species-specific body forces like electric fields individually. The only way for this relationship to be valid under all cases is if the term in brackets is exactly equal to zero. And what this does is it gives us relationships between these various multi-component diffusion coefficients. And so what you'll find is in the case where there's only two components, this relationship simplifies to show us that there are two diffusion coefficients that come out of that D12 and D21 if you work through the math, and it shows you that they're identical. In other words, in a binary diffusion, say of one gas through another or gas through a liquid, the diffusion coefficient of component 1 through 2 and 2 through 1 are identical to each other, and they have to be in order for the sum of those diffusive fluxes, the sum of the J sub A's, to be equal to 0. So in binary diffusion, there's only one diffusion coefficient that's important, and that's what you would know from basic transport phenomena. When the situation goes to just a three-component mixture, you can start to write out these expressions for each of the terms in this equation, and it turns out that there are 6 possible non-zero multi-component diffusion coefficients. So in a binary system, you have only one diffusion coefficient that's important, or that enters this expression for flux. As you go even to just one more component, add a third component, there's 6 non-zero diffusion coefficients. The criteria that this term has to be equal to 0 provides 3 relationships between them, and so that leaves 3 diffusion coefficients that would have to be fixed by experimental measurements in a ternary system. And so you go from a binary system where you only need one diffusion coefficient to completely describe that system to a ternary system where you need 3 diffusion coefficients to completely describe it, and all of which would have to be determined, for example, by experiments. And if you work through the math on this, it's a combinatorial problem. As you go to 4 components, you need 6 diffusion coefficients and so forth and so on. And what this is telling us is if you go to systems where you have many components, so if you consider the air in this room, you might consider it dominantly to be oxygen and nitrogen, but there's some water vapor, there's CO2, there is some argon in it, and you can go on down the list of the components that are in the air in the room. And if you're trying to model rigorously transport phenomena of a component through air, it's potentially has many components in it, and this will lead us in a moment to simplifications where we take complex multi-component problems and very often reduce them to essentially to effective binary transport problems. Most of the problems that we will work, even in multi-component systems, to get analytical results and results that we can compare to experiment, are analyzed based on pseudo-binary mixtures, and I'll show you how to make those simplifications. The point here is simply that as you go to more and more components, the number of independent parameters, the number of these diffusion coefficients that you would have to fit from experimental data goes up essentially exponentially. We can break the mass flux due to diffusion up into several pieces, one due to concentration-driven transport, or what I'll call ordinary diffusion, one due to pressure gradient-driven transport, and one due to so-called forced diffusion or species-specific body coefficient diffusion, and one due to thermal diffusion. We'll look at these individually here for just a bit. Pressure diffusion is important in systems where, for example, you apply a pressure gradient across a system, and this can bring about a mass transfer. The simplest example of that, which we'll look at a bit later in the course, is a centrifuge tube. So if you have components like water with latex beads or proteins or other macromolecules in it, you can put that in a centrifuge and rotate it to generate a centrifugal force, and that centrifugal force sets up a pressure gradient inside the centrifuge tube, and that pressure gradient drives mass transfer. And what it does at the end of the day is what you might expect it to do intuitively. It drives the heavier components to the region furthest from the surface of the centrifuge tube. But we'll come to that a bit later. Again, this is just the mathematical machinery in this case, and we'll recall that for the binary case, we have the results that are shown here. These the diffusive fluxes of A and B have to be equal and opposite to one another, and that translates to these generalized driving forces having the same relationship. The thermal diffusion coefficients of the components have to be equal and opposite to one another, and the mass diffusion coefficients have to be DAB and DBA have to be exactly the same. There's only one diffusion coefficient in a binary system. That's important. And so the expression that is shown in red is the reduction of our generalized expression on the first page to the situation that we would use for a binary system. And to put this in practical terms, we need to do a little bit more work on the chemical potential term, and we'll express, this is expressed on a mass basis. We'd also like to be able to express it on a molar basis for problems where we're solving mass transport problems in molar units. To convert from mass to a molar basis, we recall that the definition of a chemical potential. So we have chemical potential gradients that are appearing in this relationship, and the mass-based chemical potential is the derivative of the free energy of mixing, the free energy of a mixture with respect to the mass of component A. And we can write that in terms of a reference chemical potential and an activity. We can evaluate the derivative that appears in the flux expression as shown here. I won't belabor the math to get down to the point that's shown here. We can also put this on a molar basis, and this may be the form that you would have used, that you would have learned chemical potential when you take it in thermodynamics, and this will be the change in the free energy of the mixture with respect to the number of moles of component A. M sub A is the mass of A, and capital M sub A is the molecular weight of A. And so this provides a relationship between the molar chemical potential that you may learn in thermodynamics and this mass-based chemical potential. You can also define an activity on a molar basis using exactly the same formalism that we've shown up here for the mass-based activity, and evaluate the derivative of in a very similar fashion. What we define as an ideal solution will be one in which this criteria holds, that is the change in the log of the activity with respect to the mole fraction of A is equal to 1, and we can, that means that the activity coefficients are independent of composition. We want to put the mass flux in terms of the mole fraction and molar-based activity. We have to evaluate this term, which has only mass fraction and gradient and mass fraction in it, in terms of mole fractions. And I'm right here, the general relationship between mass fractions and mole fractions. And for a binary system, that reduces to what the result in equation 17. I'm not going to belabor in detail the algebra in the derivation that follows, but we basically can write the mass flux ultimately as shown here at the bottom of the page, and using the relationships between mass fraction and mole fraction, we can write the mass flux in terms of a gradient in mole fraction, as well as write it in terms of a gradient in mass fraction, as we saw earlier. Typically, this will reduce to standard form of Fick's law. All of the terms that are out front of the gradient in mole fraction are taken to be the so-called effective diffusion coefficient. This is what would typically be reported in experimental data as diffusion coefficient, is this entire grouping of terms, and that is shown here in terms of both the mass fraction as well as mole fraction. And what this is showing is that the diffusion coefficients that we normally use in Fick's law, these so-called DAB0, or the binary diffusion coefficients, include a contribution in them from the thermodynamics of the system. And so that's not immediately apparent from writing Fick's law just as, flux is minus the diffusion coefficient times the gradient in concentration. But if you go through a more rigorous view of this, you'll see that there are thermodynamic effects that show up in the diffusion coefficient. Those are not always important, but there are cases where these terms will essentially make the diffusion coefficients act strange if the thermodynamics of the system are not are somewhat unusual. And so the final form for our binary expression for diffusion coefficients is shown here at the bottom of the page. It includes contributions from thermal diffusion, mass concentration gradients, pressure gradients, and species-specific body forces. And again, there's only one diffusion coefficient in these systems. Another approach to describing mass transport is the so-called Stefan-Maxwell, or in more recent times, Maxwell-Stefan equations. And I'll show you how those are derived. And there are circumstances under which they provide a much easier pathway to solving mass transport problems than the way we typically apply Fick's law. And so the essential point with the Maxwell-Stefan equations is that we typically will write in the way that we have been solving these problems, we'll write the mass flux or molar flux in terms of the concentration gradient and set up and solve the problems from that point of view. The Maxwell-Stefan equation gives us a way to write the gradients in concentration as a function of flux, and then set up and solve the problems from that standpoint. And so we recall the definition of the flux in terms of the generalized driving force. This is where we started at the beginning of this section. It turns out then you have, if you were to write this expression out for a series of components. You have one of these relationships for each component, and then it has in it sums of terms that go over the generalized driving force for each component. You form essentially a matrix system of equations, and Hirschfelder, Curtis, and Bird inverted this this matrix to give an expression where the generalized, instead of the flux being written in terms of the generalized driving force, you can write the driving force in terms of differences in velocities between the components. These differences in velocities turn out to be related to flux, as we'll see in just a moment. And so if we write the molar flux using its standard definition, the concentration of a component times its velocity, we can, turns out we can write this term, the difference in the velocities of the components, in terms of their fluxes. And so this gives us an expression that writes, instead of writing the flux in terms of the driving force, we now have the driving force written in terms of the flux. And it turns out that there are certain circumstances, particularly in multi-component transport, where it's useful to have the generalized transport equation written in this form. And so we can come to we use this expression in problems where the fluxes in the system are fixed, and I show the expression for the generalized driving force here. We can simplify this first term as shown at the bottom of the page. And so this is our generalized Stefan-Maxwell equation shown in red. What you'll often see in textbooks is a simplified version of this as reported as the Stefan-Maxwell equation, and the assumptions that lead to what you'll typically see in the textbooks are that the solution is ideal, that this activity term is equal to 1, that there's no pressure diffusion, so this term goes away, no species-specific body forces, so the last, these terms go away, no thermal diffusion effects, and the result then is, that's often reported as the Maxwell-Stefan equation, is one that shows here. And it relates the gradient in composition in a system to the fluxes of the components through that system. So this will be our starting point when we go to use the Maxwell-Stefan equations and apply them to multi-component transport phenomena. The last piece of the theory I want to get to before we go back to problem solving is shown here. And this is related to the concept of effective binary diffusion coefficients. And the problem that we face, as we saw in the previous section notes, is that once we get out beyond binary systems, which are described with a single diffusion coefficient, as we get to more and more complex systems, the number of diffusion coefficients you need to describe the transport phenomena completely goes up enormously, and the complexity of solving those problems go up enormously. And it turns out that there's a number of practical situations where one can reduce a multi-component transport problem to an effective binary transport problem. And I want to run through just a few of those cases because they turn out to be of enormous practical importance. And so the definition of what we call a mutual diffusion coefficient or a binary diffusion coefficient is given here for in molar coordinates. That is, the flux is minus the molar concentration of the mixture times the binary diffusion coefficient times the gradient concentration of A. And the second term over here is essentially the convective or frame of reference term that accounts for all of the flux of component A that is not due simply to a concentration gradient. So this will be, pressure-driven flow and any other type of convective motion. Now, this result, if you compare it to what we've just waded through in terms of theory, it assumes a number of basic features that are shown here, and it turns out that these are often very good assumptions for many of the practical problems that one would want to attack. And so there's a number of important practical considerations where it's useful to define by analogy an effective binary diffusion coefficient, what I'll call the diffusion coefficient of A in a mixture in a multi-component system that has many components, more than two. And so the way we will define this effective binary diffusion coefficient is to write an expression that looks like the rigorous binary flux expression here, but to include the fluxes of all components in the mixture in this convection term. We can then write the gradient in composition of A as shown here by an algebraic rearrangement of this result, and we can compare that result to the Stefan-Maxwell equation that we've just gone through, and we can then identify these effective binary diffusion coefficients in terms of the fluxes and the diffusion coefficients of A and B. We're going to make the assumption that the molar and mass average velocities are equal to one another, and that turns out, without going into a great deal of detail about it, that turns out to be a good assumption for many of the systems that we'll be interested in it from a practical point of view. There's often very little difference between these effective velocities. It's also helpful in what we'll look at in just a moment to recall that the average molecular weight of a mixture is defined as the mole fraction weighted average of in a mixture. And if let's see if I can get back here. If the system is dominated by one component, like component 1, then the average molecular weight will be just that of component 1. And so we'll look first at a number of limiting cases. And so the first is where you have trace components 2, 3, 4, n diffusing in nearly pure ones. And so you can consider, for example, a glass of water. It has in it not only H2O, but it has H3O plus, OH minus, and at ambient conditions, a glass of water sitting out on the table here will have dissolved in it all of the gaseous components that are in the air that's in contact with it at equilibrium. And so this will include nitrogen, oxygen, argon, whatever else, CO2, whatever is in the air. The CO2 will speciate further into carbonate and bicarbonate. All of these components are at very, very low concentration in water, except the water itself. And that provides an enormous simplification when you go to model, for example, the transport of bicarbonate through water, the transport of oxygen through water. You don't have to include all of the other components that are there, and the reason for that is going to be shown here. What it turns out is that in that case, the diffusion of any species, for example, oxygen, bicarbonate, OH minus, H plus, etc., the diffusion of any of those species through that mixture is essentially equal to the binary diffusion coefficient of component A through the dominant component. So the diffusion coefficient, for example, of oxygen in water that's equilibrated with air and has all of these, has a whole laundry list of various species in it, the diffusion coefficient of oxygen in that mixture is equal to the diffusion coefficient of oxygen in pure water. This is the basic idea. And likewise for nitrogen, likewise for H plus, likewise for OH minus, you go on and on down the list. And the proof of that is to write the effective binary diffusion coefficient as we've derived it back here on in equation 5, is to write that expression, and then to start writing out the terms in the in the numerator, and considering the limit where the mole fractions of all of the components except gives some of the most widely used approximations in solving diffusion problems. One is the assumption of no convection. So we start in either mass or molar units with our general continuity equation, and we write the we can write this this equation also is shown here in terms of total flux in either mass or molar units, and under the approximation where there's no convective motion, then the total flux and the diffusive flux are equal to one another. diffusion's the only game in town. And with this simplification, we can write the continuity equation as shown here in mass units and molar units, and introduce Fick's law in either mass or molar units, where these diffusion coefficients we might recall can have a thermodynamic dependence. Typically that thermodynamic dependence is simply lumped in with the diffusion coefficient to give us an effective binary diffusion coefficient. That's what we normally use in Fick's law. And so an ideal solution where either the total molar concentration or density of a mixture is constant, then you get the familiar form of Fick's law both in mass-based units as well as molar-based units. And then if the density is constant and the molar concentration is constant, you'll find these are the forms of Fick's second law of diffusion. These are the most widely used forms of the diffusion equation, the transient diffusion equation, in the absence of chemical reaction. And I will point you at this point to a book by John Crank called The Mathematics of Diffusion. And it's an excellent resource for solutions to the diffusion equations that are shown here in equation 9. So virtually all of the analytical solutions, or a huge number of the analytical solutions to the diffusion equation, are given in this book by John Crank. And he points back to an analogous book that was written somewhat earlier by Karslaw and Jaeger called The Conduction of Heat in Solids. And it makes a real close connection between the analogy between heat and mass transfer, because there is an analogous expression for heat transfer where concentration is replaced by temperature and diffusion coefficients are replaced by thermal conductivity. And so there's a whole book of solutions to that equation in The Conduction of Heat in Solids. And at the preface of The Mathematics of Diffusion, John Crank says, I'm not going to repeat that here, just substitute temperature, concentration for temperature, and diffusion coefficients for thermal conductivity. But this is a great resource if you're working with mass transport, and I would highly recommend it. We work through the assumption where a bit more general view of or version of mass transfer is one in which you do have convective velocity in the absence of chemical reaction, and where you only have concentration-driven transport. An ideal solution, you get the so-called convection diffusion equation. This will be the starting point for us for solving problems where you have both mass transport driven by convection as well as by diffusion. And you'll find again, this is the final form of the convection diffusion equations, often the starting point for solving practical problems for us in this area. So that's the end of the theory section, and then I'd like to come back to some problems that we've looked at previously, just theoretically, and start to apply numbers to them, because I believe that it's really important that as you begin your journey in this field and learning the basics and advanced mass transport, that at the end of the day we're always looking back to practical problems and how do you apply this in a way that makes sense in reality, and how do you use this machinery to solve practical problems. And so we'll start with a problem that we've already looked at in terms of a brief analysis, and that's a wetted wall column. And so essentially we have in this example a tube, and I'll make it in this case 13 centimeters long and and 2.8 centimeters wide. And we're flowing a gas up through it that has a low level of chlorine in it that we're trying to strip out. And we're doing that by flowing water down the inside edge of the tube. And then when the water contacts the gas stream with chlorine in it, chlorine is much more soluble in water than would be typical gas components like oxygen and nitrogen that you might find in air. And so the chlorine will dissolve preferentially into the water and be stripped out of the gas phase. And so we want to model how much chlorine you can remove from the gas phase with a given amount of water, and the thickness of that water layer on the inside of the tube is going to be delta, and that's going to be much less than the tube diameter. We're going to neglect the effect of the chemical reaction between chlorine and water and look really at the physical solubility of chlorine in water, the value of which is shown here at ambient conditions. Diffusion coefficient of chlorine in water has been measured, and the value is given here. And we're going to calculate the chlorine absorption rate when the average velocity in the water is the value that's shown here. We can that of course is a variable in the model, and we can change that in order to change rates of adsorption and so forth. But we just set up one problem where we run through both the model and the detailed calculations to show you how to get to kind of bottom line answers in this area. You'll recall that we treated this problem earlier as in the following fashion. Since the thickness of the water layer is much less than the diameter of the tube, this allows us to essentially unwrap that tube and treat it as a flat sheet with water flowing down that sheet. You'll remember the criteria for that we derived early on, and so when the radius of this tube is when the thickness of this layer is on the order of 1/5 of the radius of the tube or more, then treating this as just a flat plate problem is a good assumption. If you look back through the notes, you'll see where we derived that. In this case, we're very far into that regime, and so we'll retreat this as a vertical falling film that has a width W, which is just pi times the diameter of the diameter of the tube. And so you have essentially turned this problem into a flat plate of width W and the length we've already given, as well as the thickness of the water layer. I've drawn in the velocity profile as well as the chlorine concentration profile in that mixture. We'll consider a case where we're in a laminar flow and it's a gravity-driven flow field. It'll be useful for us to define the average velocity, because we can then relate the one of the specifications in the problem was the average velocity had this value, and so we can define the average velocity as just the integral of the velocity over the width of the film, and so the average velocity is 2/3 of V max. The maximum velocity is given out here at the gas-liquid interface. We can, in this case, you'll see in your textbook that we can, in this sort of flat film situation, define the Reynolds number for this flow as shown here, and the thickness of the layer is given using the expression shown here, and so we can derive the thickness of the layer of water. It's on the order of 0.25 millimeters, and we can see immediately that this assumption that the thickness of that layer is much less than the diameter of the tube is easily satisfied. You also calculate from that the Reynolds number, and it turns out to be 156. For falling films, the transition from laminar to turbulent flow is about 1800, so we're in a good situation in that we're in a laminar flow regime, so the assumption that the velocity flow is parabolic like this is correct. And we start this problem very typically now using the more general machinery that we've developed by looking at the mixture continuity equation first. And so I write it for the case where this is the mixture continuity in the water phase where there's no chemical reaction. And we are going to consider the steady state operation of this device. And so the transient term goes away. And the only term that's left, and that the density of the system is essentially constant, is that the divergence of the velocity is zero, and that means that dvx dx plus dvz dz is equal to zero, since we have velocity components in the x direction. It's very typical in these problems to assume that the bulk of the velocity in the z direction is due to the convective flow, gravity-driven convective flow of water, and so that Vz depends only upon x and not upon z. In other words, you don't absorb enough chlorine from this gas phase to markedly change the velocity of the water, and that would be typical of the way these gas absorption towers would operate. And so if the velocity in the z direction is only a function of x, then that leaves us with the result from continuity that dvx dx is equal to 0. So that's as far as we can get from that. We can then write an expression for continuity on each of the components. So we have water and chlorine. It turns out to be a little more useful to work with the chlorine continuity, because we're trying to model the chlorine absorption rate, and so this gets us to that endpoint faster. And so here we write the convection diffusion equation, again with no chemical reaction at steady state. The convective term goes away. We use Fick's law to model the diffusive term as shown here. And we get to the general relation that's shown at the top of the page. So we have a term that relates to convection of chlorine, component A, that's perpendicular to the flow field, a term that's related to convection that's parallel to the flow field, and then diffusion both through the film and diffusion in the direction of fluid flow. We can make an order of magnitude analysis with the knowledge that the velocity in the z direction, that is in the direction of fluid flowing down the wall of the tube, is typically orders of magnitude greater than the average velocity fluid flowing through the film, that is chlorine flowing through the film into the water. And also that the length of this film is much greater than its thickness. With these two specifications, you can show by order of magnitude analysis that this term is much greater than this one. That is, that the dominant term for convection in this problem is convection down the wall of the film. That is, that convection into from the gas phase into towards the wall is negligible. And also you can show that the concentration gradient in the x direction, see our picture again, the concentration gradient in this direction is much greater than the concentration gradient from the top to the bottom of the film, and that comes out of the fact that this film thickness is so much less than the overall height of this column of or sheet of water. And so that introduces great simplifications to this problem, and essentially what you come down to is a result that is that's shown here. And it says that the rate of transport of chlorine into this film by diffusion in the x direction, that is from across the liquid film, is equal to the rate of chlorine transport by convection down the wall of the film. In other words, chlorine diffuses from the gas phase into the film in the X direction, and then at steady state, any chlorine that diffuses into that film has to be taken away by the convective flow of water. So there has to be a balance between the mass transfer in the down the length of the column and balancing the diffusion that occurs for chlorine being brought into that film. We have an expression for the velocity profile. This comes from fluid mechanics, and you can find that derived in your textbook in the earlier chapters on fluid mechanics of falling films. But the final form of the convection diffusion equation is shown here. We have boundary conditions that at x equals 0, that is at the gas-liquid interface, that the concentration of chlorine is equal to its equilibrium concentration. At the wall, we have no flux of chlorine through the wall, and we treat the water as being chlorine-free at the top of the column. We can simplify the problem further by considering the time scales in the problem. And so one of the time scales is the time scale for chlorine diffusion through a film of thickness delta, and I'm going to show you how to derive this in another lecture or so. But essentially the time for chlorine to move through that film of liquid water is given by the square of the thickness of that layer divided by the diffusion coefficient, and that's on the order of 48 seconds. The other time scale that's in this problem is the contact time of fluid with chlorine in the column. So the water is flowing down the column, and it is in the column on average for a time of the distance over which it flows divided by the average velocity of the water. So you plug those numbers in. That turns out to be on the order of less than a second. So look at the picture here. The water is flowing down the wall of the column. It's in that column less than 1 second. It takes almost a minute for chlorine to completely saturate that liquid layer by diffusion. So there's a large separation in these time scales. What it means is that in the brief period of time that the liquid is flowing down the wall of the column, in the brief period of time that it's in contact with chlorine, you'll only get a small amount of chlorine penetration into that liquid film. And that means that you can turn this expression around and calculate the penetration depth based on the contact time of the liquid, and it turns out that the penetration depth is on the order of, I guess that would be 31 microns in a film that's 1/4 of a millimeter thick. So the chlorine only, in the time that the water is in the column, the chlorine only penetrates a few microns into the top surface of that layer of water. And that leads to an important simplification. We can write, we can ask what is the velocity that the chlorine that has penetrated furthest into this layer, what is the velocity that that chlorine sees? And it's 98.4% of the maximum velocity. So for all intents and purposes, as the chlorine is diffusing into the water that's flowing down the wall, it's seeing essentially the maximum velocity because it's only diffusing into that thin layer right at the gas-liquid interface. And that allows us to make the assumption that the velocity here that appears here is essentially equal to the maximum velocity and is a constant. This simplifies this problem enormously because now it's just a second order differential equation, partial differential equation, and the solution is given here. I won't belabor getting all of that, but essentially you can, this is exactly the solution that we found to a transient diffusion coefficient, a transient diffusion problem earlier. We can determine the rate of absorption of chlorine using a jump chlorine mass balance, and that's shown here. Essentially, we write out the jump mass balance. The the chlorine, the interface is not moving in this case. So although there's fluid moving in the down the wall of the tube, U in this case is the velocity here. Ux is the velocity of the interface itself in the x direction, and that is 0. So these terms go away. We can then write the flux of chlorine essentially in terms of the diffusion coefficient. There's times the gradient in concentration at the surface. We have an expression for the concentration profile, so we can evaluate this derivative at the surface, integrate it across the entire length of the tube to get the mass transfer of chlorine into that entire liquid film, and the result is shown at the bottom of the page. And essentially what it comes down to is that the rate of adsorption of chlorine is equal to a term which is the essentially the rate of adsorption if the water were completely saturated with chlorine times a term that gives you the what amounts to the fractional saturation, and that term depends upon the diffusion coefficient. Essentially depends on the how much contact time the fluid has with the gas has with the fluid. We can also write that in terms of we can define it in terms of an effective mass transfer coefficient, if you do that and combine this expression with the one on the previous page, you'll find that that mass transfer coefficient for a falling film is given by this expression. So it's a classic result that you'll find in textbooks on mass transfer coefficients for gases absorbing into falling films, and this is where it comes from. For our case, we can calculate the exposed surface area, calculate the mass transfer coefficient, and then calculate the absorption rate of chlorine. And so this shows you how to walk through a practical example of a problem that we solved theoretically a bit earlier, but now to put numbers with it, to start to think about differences in time scales that lead to simplifications that make the problem much more tractable. And so I'm not going to start another section of notes now, but I'm going to wrap things up here.